The specific gravity of ice is 0.917, whereas that for salt water is 1.025. What fraction of an iceberg is above the surface of the water? When they talk about specific gravity, that's just a special way of measuring density, where 1 would be the density of pure water. And we've talked about this a little bit in class, how like 90% of an iceberg is below the water because it has a specific gravity of 0.9. It makes the math really easy. This is a little bit trickier because you got this 1.025, but I wouldn't let it freak you out too much. So here's a really simple way to think about this. The density of ice divided by the density of salt water gives you this stuff. And it tells you that the ice is 89.5% as dense as the water that it's under, which means 89.5% of it is required to float. And that's really about it. You got to have 89.5% under the water in order to pull that off. That's actually all you need to do there. But if you got stuck on that one, another solution would be to simply construct something like a 1 meter by 1 meter by 1 meter iceberg, and then make the forces equal. So make the force of gravity equal to the buoyant force, and then you can calculate how much volume you need to be exposed in order to get enough buoyant force to counteract gravity. But you would end up with the same percentage of the thing. Yeah. If wind blows at 30 meters per second over your house, what is the net force on the roof if its area is 240 square meters? This one is talking about Bernoulli's principle because you've got pressure with a fluid that's in motion. The air is in motion over something, so we need Bernoulli's equation. So here we've got Bernoulli's equation, which looks enormous, but it's really not that big of a deal. It's just energy. You can sort of think of it as the work, which is kind of done through pressure, plus the kinetic energy, 1/2 density velocity squared, plus the gravitational energy, rho gh. So basically this thing is just conservation of energy with density and pressure instead of some of the other stuff. And since it comes from conservation of energy, that means it had better be the same in both places for this fluid. Now we're talking about wind blowing over the top of the house, but on the bottom of the house it's not blowing, which means there has to be a pressure difference. But the key thing here is recognizing that this term does not matter, because the air above the roof is pretty much at the same height as the air below the roof. It's not really a big difference. So really all we care about is this stuff, the pressure and the 1/2 rho v squareds. All right, so plugging things in one at a time. First, we're going to look at the air underneath the roof. It's going to have the usual pressure because nothing's going on. So 1 atmosphere, 10 to the 5th pascals. Plus the velocity term, so 1/2, the density of air is 1.22, times the velocity, which is 0. So this thing actually dies, and we don't care about it. Now we look at the stuff going on over the roof. You've got pressure. We don't know what it is. We're kind of looking for it. Plus the 1/2 density times velocity squared term. All right, working through it a little bit more. We got 10 to the 5th equals the pressure on top of the roof, which I'll call P2, plus 549. That's what I got simplifying this term. And I'm just going to rearrange it a little bit to get the pressure under the roof, which is 10 to the 5th, minus the pressure over the roof, is equal to 549. And check it out. We've got the pressure on the bottom minus the pressure on the top, which means this number tells us the net pressure. It's the difference in pressure between the top and bottom, and that's what we're after. Just like with forces, we're always looking for the net force. If you look at the stuff pushing up and pushing down, we can do the same thing with pressure. So now that we've got an expression for the net pressure, we can use that to attack the force. Remember, pressure is equal to force divided by area, so net pressure equals net force divided by area. And I just rearranged this thing to get net force by itself, and it's just equal to the pressure times the area. And we figured out both in the problem. So you get 129,000 newtons. And remember, there's 4.5 newtons to a pound. So if you divide that by 5, that's how many pounds of upward force you have on this roof. And now you can believe why some tornadoes lift the roofs off of Walmarts.